Good afternoon, everyone. It is my distinct pleasure today to welcome our guest of honor, Dr. Jana Houser. Dr. Jana Houser is an associate professor in the Department of Geography. She is a meteorologist by training, and she has her bachelor's degree in meteorology from Penn State University, a master's from the University of Oklahoma, and a PhD from the University of Oklahoma. Working with someone who is very well known in the tornado community. And so it's great to see such a diverse audience today in terms of age ranges, because when it comes to topics around severe weather and tornadoes, I think many of us became passionate about the weather at a very early age. And Dr. Houser is one of those who took her passion, her interest from a young age, and turned it into her profession. And so for the younger members of the audience here, or those who are interested in embarking on a second or third or fourth career, pursue your passions. And you can be up here and talking about exciting things like tornadoes and the movie Twisters in the future. Dr. Houser's research has been funded by the National Science Foundation, and she's received a very large grant from The Ohio State University to acquire a mobile Doppler radar, which will facilitate some of the study of the genesis of these events and other great data collection in the field. Dr. Houser also is someone who spends a lot of time in the field pursuing data collection, and so that will factor into her talk today about Twisters and how she was included in the credits for that movie. We're very honored to have her joining our department here at The Ohio State University after she worked at Ohio University for a number of years. She's an award-winning teacher and a well-known researcher in this area, so please join me in welcoming Dr. Houser.
All right, thank you, Stephen, for that lovely introduction. All right, I'm gonna do a mic check. Can you hear me on this one? Good, good, good. All right. Well, thank you so much for being here. I can't see your faces because I'm blinded by the light right now. But before the lights went down, I saw so many people of so many different ages. I'm just thrilled. So thank you for spending your Sunday afternoon with me here today. So yeah, I'm going to talk about tornadoes. And the way I was thinking I would go about doing this is to present to you the questions that I am commonly asked. So I get asked questions by the media, I get asked questions by people on an airplane, by kids, and so I thought this might be a good opportunity to address the majority of the big questions that I get. So hopefully some of your own questions are answered as we go forward and go through this next hour. So the first kind of question, so I have a little bit of method behind the madness here, where there's a little bit of a storyline that we're following. So in order to understand tornadoes, we need to be able to understand the kind of atmospheres that tornadoes form in. So the first question is, what kind of atmospheric conditions are needed for tornadic storms? So the two most fundamental ingredients for storms that produce tornadoes, and actually any kind of thunderstorm that you might get, include warm air at the ground and moist air at the ground. So we need those two parameters in combination together so that we can get these really big billowy thunderstorm clouds that we see. And then there's a third thing, oops, I'm pressing the wrong button here. There's a third thing that kind of comes into the equation here too, is that not only do we need warm, moist air at the ground, but we need to have cold air above it. So you kind of have like an atmospheric sandwich where you have really warm air on the ground and moist air on the ground, and then above that we have this really cool air. And the reason why we need that is because warm, moist air is buoyant. It's lightweight in comparison to the cold air above it. So we have this situation that we call instability in the atmosphere, because the cold air actually doesn't want to be there. It wants to be at the ground, and the warm air wants to go up. So when we have this sort of weird atmospheric temperature sandwich, it's called instability. So that creates this condition which allows thunderstorm updrafts to form. Okay, so do thunderstorm updrafts form by themselves? Generally not. And an updraft, by the way, is just this channel of really warm air that comes up and basically is the engine of the thunderstorm. You visually see these updrafts in the thunderstorm clouds that you can look out your window and see where it's all billowy and kind of poofy looking. That's the thunderstorm updraft. But typically, air at the ground doesn't want to rise just spontaneously on its own. So we need another ingredient that we refer to as a forcing mechanism. This forcing mechanism you can think of as kind of like a little nudge. It's almost like somebody lifting the air up just enough to get it to freely rise. And then when it freely rises, it can explode and form those really big billowy clouds. Forcing mechanisms can take a variety of different shapes and forms. Sometimes they occur at the surface in the context of a front, oftentimes actually a warm front in the terms of tornado storms. But we also get storms that form along cold fronts. Those are less likely to be tornadic, though. Sometimes you get moisture fronts called dry lines, and sometimes our forcing mechanisms are actually considerably higher than the ground, and they're occurring as these little waves of energy high up in the atmosphere. And what happens is as these little waves of energy move through, they actually create uplift because there's energy that's kind of, and winds that are kind of blowing out of those high up in the atmosphere. Sometimes it can even be a mountain, or it can even be the cold air that was formed by another thunderstorm earlier in the day. So all of these things can work together to cause that initial nudge to get our air moving upward. Our sixth ingredient here, so we said surface warm temperatures, surface moisture, cold air aloft, and those three combine together to create our fourth, instability. And then our fifth was what we were just talking about with the forcing mechanism. And our sixth ingredient now is really, really important. This is the one that differentiates between just your everyday ho-hum thunderstorm and the thunderstorms that get really violent and form tornadoes. And this ingredient is called wind shear. This is when you have winds that change in both speed and direction as you go up in height. So at the ground, your winds might be coming from this way, and higher up, they're coming from this way, and they're even faster. So you can imagine if we have this contrasting direction and speed of air, what that does is it actually causes the air in the whole atmosphere to spin horizontally, kind of like a bike tire is spinning. And ultimately, that's what helps our thunderstorms rotate themselves, and I'll talk about that in a few minutes. But this is, again, this is the critical ingredient that separates non-producing storms from tornado-producing storms. All right, our next ingredient, I promise we're getting to the end here. Our next ingredient is what we refer to as the cap. And this might be a little bit counterintuitive. The cap is actually a shallow layer, so if the surface is here and high up in the atmosphere, like where airplanes fly is up here, the cap occurs roughly about here, a little bit above the ground, but not too high up. And what this is, it's a layer where air actually increases in temperature with height. Now that might sound weird because what I just said before is when we need colder air above the ground. But what this cap does is it's kind of like squashing our storms. It puts a lid on that warm surface air and allows that warm surface air to heat up more and more and more and more and more until all of a sudden it's warm enough that it can actually bypass that cap, and then it creates explosive storms. So when we have a cap, we tend to prevent thunderstorms from forming too early in the day. If they form too early in the day, they don't maximize daytime heating, and the storms don't get as vigorous and as energized. So when we can put that cap on, we allow everything to really get really hot and really energize itself. So when that cap breaks, then all of a sudden we see very strong thunderstorms develop. And what I'm showing right here is actually a vertical profile of temperature in the red, and then dew point, which is our moisture parameter, in the dashed black. And this is taken by a weather balloon. So the weather balloon starts out at the ground, and it goes up in the air, and it records the temperature. And so we're seeing where the red line kind of goes this way, our temperature is decreasing with height, and then it's nosing out right here, which means that it's actually increasing with height. And then above that, we have very cool temperatures too. So this little nose in our vertical profile is what we refer to as the cap. I told you we were getting near the end. So, summary of our ingredients: that warm, moist surface air, cold air above that, that instability, forcing mechanism, change in wind speed, and this stable layer just above the ground. So once we have this this set of ingredients in place, we're now ready to start to produce the thunderstorms that ultimately produce tornadoes. So another question I'm very commonly asked is, why is it that the United States is the world's most tornadic-prone area in the entire world? So what I have here is a hotspot analysis. Now, these don't indicate individual tornadoes, but they indicate kind of on a broader scale where tornado activity is maximized. And we can see that the US is pink, and those pinks are the hotter colors indicating that we have the most tornado activity here. And Central Europe has a little bit of tornadoes, so does the coast of Australia, and even places like China and Japan. And Argentina actually has a pretty good amount of thunderstorm and tornado activity too, but nothing beats the US. So why is it that this is the case? So here's where we have to turn it over to geography. So I'm in the Department of Geography. Geography is a physical science here, and we're bringing everything together. So in this context, the United States has a very special set of geographic conditions that really promote tornado events promote them to occur here. So the first one is this Gulf of Mexico. So I'm sure we've all pretty much heard of the Gulf of Mexico, but what the Gulf of Mexico does is it provides warm, moist conditions. So it's pretty far south, and as a result, that water in the Gulf of Mexico is very warm. And if we get a little bit of air that's moving up from the Gulf of Mexico, we transport that warm, moist air to this part of the United States. Another thing that we have to consider is, interestingly, a part of Mexico called the Mexican Plateau, which is here and kind of extends a little bit even further down than what the circle is. And what happens in this case is the Mexican Plateau is hot and dry. And oftentimes we get winds that are blowing from the southwest above and right kind of next to the land there. And as the winds move from the southwest, the ground gets lower as you go to the east, and this is responsible for the formation of our cap in this part of the country. So this provides that warm air that's just above the surface. It also promotes the formation of a moisture gradient that's called the dry line, which separates that hot, dry air in the west from the cooler, moist air that's coming up from the Gulf of Mexico. And the dry line is critically important to thunderstorm formation that oftentimes goes on to produce tornadoes in the central part of the United States. All right, another feature that I just alluded to is the fact that we have the Rockies here, and the terrain slopes up across the Central Plains towards the Rockies, away from the Mississippi River. And this provides two things. Again, as I indicated, it helps form this dry line. It helps create this descending elevation to give us that hot, dry air as the cap right here. And it also promotes another feature called the low-level jet. And this is dynamically very complicated, so take my word for this. If you want to come and sit in on the class where I teach this in mesoscale next semester, send me an email. I'm happy to oblige. But let's just say for the time being, take my word for it, the fact that we have the mountains out here actually creates a strong current of air that blows up from the south in the summertime and springtime months there. And that air is, again, kind of at the same level as that cap. So just a little bit above the surface, and that helps to promote near-ground rotation that ultimately can get tapped into for tornado production. And then we have the Rocky Mountains themselves. The Rocky Mountains are very important because on the eastern side of the Rockies, what ends up happening is we have the formation of low pressure systems. We have troughs aloft that come in from the Pacific. So these are these wavy features that I alluded to before. They come in across the Pacific. They kind of lose the surface features lose their steam as they're hitting the Sierra Nevadas and the Cascade Mountains. But the troughs, after they cross the Rockies, still have energy and then produce low pressures that can range all the way from the Texas Panhandle clear up into Canada here. And typically in severe storm scenarios, you have this Rocky Mountain low that forms just to the east side of the Rockies in Colorado or northern New Mexico. And what this low does is it goes and forms, sorry, thought I had another arrow there, but apparently I don't. So the lows have circulation around them that's going counterclockwise. And so when you're east of the low, that acts to pull up this warm, moist air from the Gulf of Mexico. So can you see we're working in each of the ingredients that we were talking about just a few minutes ago and explaining now how the conditions in North America are especially special for creating these tornadic storms. All right, and then next we have this large landmass up here called Canada. And Canada is important because that cold air gets transported down, and it's transported down sometimes a little bit at the surface, but also aloft in the form of these big troughs in the jet stream. And those troughs provide energy to support the low pressure development. It provides cold air to get that instability going, and it provides strong wind currents aloft, which promote that vertical wind shear that we need. So all of these things together are really what are responsible for making the central United States in particular this hotbed for tornado activity. Okay, so we're setting the stage now. How does a tornado actually form? So we've set up these environmental conditions. We've talked about how the central US can really bring all of those conditions together. But how do we actually get a tornado to form? So first, we need to have a special kind of thunderstorm that's called a supercell. A supercell is special because, remember I mentioned that updraft, that channel of upward moving air, which basically is the engine to the thunderstorm? That whole thing can rotate. That rotating updraft is called a mesocyclone, and this is what differentiates supercell thunderstorms from your everyday other kind of thunderstorm. So, fun picture of a supercell, eye candy here really, but these things are very much, they're very impressive, and they can be pretty scary, and sometimes they even look like otherworldly, like UFOs. So here's another one. So in this case, we can actually see, here's the bottom of the updraft. The updraft is, again, that sort of billowy part of the cloud here. And you can even see there's some little striations in the clouds here that suggest kind of a helical motion to the air as it's rising up through the storm. So how does this happen? Well, I mentioned wind shear, and I said that wind shear was really important. So I did that little hand thing here where we got air going this way at the ground and this way above, and that creates this spin, right? So if we have spin like this in the environment, once we get an updraft in that environment, what that updraft does is it takes the spin that's oriented this way and it basically tilts it upwards this way. So instead of going like this, it goes whoop and then spinning like this. So that upward motion causes the entire storm to rotate. It derives that rotation from the environment, just basically like what this is showing there. And then we have a couple of little other figures that show this. So this is kind of putting that rotation in the context of an actual picture of a cloud here. And this is a numerical simulation, so basically a computer simulation of a supercell. So we have air that's rotating like this, and then it gets sucked up by that updraft, and then the whole updraft rotates to form our mesocyclone. All right, so one of the ways that meteorologists are best equipped to identify these storms is through radar. And this is a picture of a radar image of a supercell. So we're looking at this storm here, and there's some pretty interesting, unique characteristics to supercells that make them prone to produce tornadoes. So if you notice, I have a little bit of a white arrow here. This white arrow indicates the location of that main storm scale updraft. So this is where all of the air is coming up. It gets sucked in from this clear area to the east and the south of the storm and gets ingested up here. And then we get a whole bunch of precipitation that kind of blows off towards the east as a result of that really strong air current aloft that's kind of oriented from the southwest to the northeast here. But because our updraft is rotating, we also get some of that precipitation to wrap back around and form what's called a hook echo. So if I took that arrow away, you could sort of see this interesting little like hooky appendage, almost like a bird beak or a fishing hook here. And this physical structure, the actual structure of the rain and the precipitation around the updraft is very important. So what happens is once you get this storm to form, you get downward moving air kind of all along this leading edge here. And that downward moving air is caused by cold air that forms from evaporation. So the rain falls through the air and it causes cooling. Cool air, as I mentioned earlier, is denser than warm air, so it sinks. that coupled with the fact that the physical rain, like if you turn on a kitchen sink, sometimes you, or your shower, sometimes you feel that downward moving air. The exact same thing happens in the real atmosphere. So we get this downward moving current of air basically along that entire edge of the storm here. Now, just outside of that edge, we have upward moving air that's warm and moist from the environment. So this combination of downward moving air next to upward moving air creates spin, again, like this, that's localized and close to the ground. So we're starting to set the stage for tornado formation. So what happens next is this air that's spinning now down by the storm. So I kind of cut out and made things a little bit less visually crazy. This blue edge basically represents the front end of the storm here. Our updraft is given right here, and this blue line here shows that outline of the hook echo. So that spin that's created by the storm now gets wrapped into the backside of the storm around the hook echo and gets sucked up into the updraft. And again, very similarly to what happens with the environmental flow, that creates rotation. But the difference now is that rotation's at pretty low levels. So we're talking, instead of like midway between where this ground and airplanes fly, now we're talking again kind of like at that lower layer, couple hundred meters or so above the ground. And that creates what we refer to as a low-level mesocyclone. So here's a really nice picture of an ominous-looking low-level mesocyclone with a wall cloud here. And so our updraft is basically through here. You can see that opaque area here is actually where the rain is falling. So we've got the downward moving air there, upward moving there, that spin, and then it basically gets sucked around the backside and causes this low-level rotation. So our first ingredient, once we have a supercell storm that forms, our first ingredient is this strong low-level mesocyclone. All right, I think I covered everything I wanted to cover there on the words. So then the second thing that we need is we need near-ground rotation. So if you look closely, this might not look like a tornado, but if you look closely, we can see some either dust or maybe cloud debris or something like that at the ground here. We absolutely need to have rotation that's at the ground before a tornado ever even forms. This forms separately from the process I described before. Although there are several different hypotheses for how this near-ground rotation comes to be, and they may all be right or they may all be wrong. So this is an area of the science that we're still a little bit unclear about, and we're unclear about it because our observations are it's very difficult to get observations of what's happening right at the ground. Radars don't tend to do very well there because you have things like trees and hills and phone poles and houses and stuff in the way. So we tend to be able to look at basically, you know, this part of the storm, but what's happening right there, we can't really observe very well with radars. And we don't have a very good network of other options, really. Everything else is kind of points. So you might have something stationed here and something stationed there, but then we miss everything else that's happening in between. So there's a little bit of an observational gap here, which is contributing to our question mark, really, about where this rotation comes from in the first place. So there are several hypotheses. One is that you have a sudden decrease in winds as a result of friction at the ground. So the winds basically grind to a halt or close to it, close to the ground. And immediately above that, they're very fast. So that, again, can create that spin like this. And then if you put that in the vicinity of an updraft, and actually I haven't talked about it, but there's a downdraft back here too. So that downdraft is caused by slightly separate processes. But the interface between that downward moving air and that upward moving air here can cause, again, a tilting to occur at near ground levels now to get that rotation very close to the ground. All right, so putting the story together, how does a tornado actually form? So one, we need this low-level mesocyclone that forms from storm-generated rotation. That rotation actually drives upward motion into it from below. So what happens is the air is moving very quickly, and it actually creates low pressure in the vertical. And then underneath that, very much like a bike tire, if you puncture a bike tire, it sizzles air out. The bike tire is at high pressure, which is like underneath, and the environment is at lower pressure, which is like our mesocyclone. So we actually drive upward motion into that low-level mesocyclone from below. And if we have low-level near-ground rotation present, that upward motion can concentrate that rotation underneath that low-level mesocyclone and then the low-level meso pulls the air up. So believe it or not, tornadoes form from the bottom up, not from the cloud to the ground. And this is a really nice sequence of images here that kind of illustrates that. We have a rotating wall cloud at this point in time here. And then a little bit later, we can actually see something kind of spinning down here at the ground. But if you look up, you don't really see a funnel cloud. And then we see that that funnel is actually kind of going up in this case, or that debris is going up. And then finally, a little bit later, we actually can see the visual of the funnel cloud. So it's kind of counterintuitive to what our brain thinks, because we tend to look at the funnel cloud and we focus on the funnel cloud because that's what our eyes see. Our eyes can't see the invisible rotation unless that rotation is coupled with debris that's already present on the ground. So yeah, the difference here is that the funnel cloud is forming as a function of the vertical behavior of temperature and moisture as you go up with height. And that's not always necessarily needed. You can have a tornado without having a funnel cloud. So, all right, I'm going to get on my podium here. I've got the floor. Tornadoes do not touch down. They do not touch down. Save the touchdowns for the football field, everybody. It, unfortunately, is part of our nomenclature. Everybody says it. But I will humiliate you if you say touchdown in my presence. So yes, tornado, I'll be kind, I promise. So tornadoes don't actually touch down. They form from the ground up. And if there's one thing I want you to take away from this lecture, that is this right here. So please, next time you hear touchdown, you need to say, oh, wait, hold on. I actually heard this talk, and tornadoes don't touch down. So spread the word, my friends. Okay, so why is it so hard for us to predict tornadoes then? Well, it's so hard because of the really specialized and specific requirements that tornadoes have in order to form. And unfortunately, it's really hard to know when and where these requirements are actually going to be met. So if you think about a storm that's capable of producing a tornado, that storm might last for 2 to 4 hours. And then in that 2 to 4 hour lifespan of the storm, it only is producing a tornado for like 10 or 20 minutes of its lifetime. So what is special about that 10 to 20 minutes? And the answer is, I don't know. We don't know yet. So there's something that creates these conditions at specific times and at specific places, but we don't always know when and where that's going to be. Similarly, we oftentimes have environments that are broadly supportive of tornadic cells. So we're looking at, states, multiple states sometimes, where you could have tornado-producing storms based on the environmental conditions. And you might have 10 storms that are forming, but out of those 10 storms, only 2 of them actually produce tornadoes. So again, what is special about those 2? And again, the answer is it's not always clear. Tornadoes are very sensitive to local conditions, and they're very sensitive to even things like terrain and land cover, so how much friction is at the surface. These things end up actually being important. All right, so here's an example. This is from a storm chase that I was on in Kentucky. Kentucky's up here, Tennessee's down here. So all of these little blobs here, these are all supercell storms. Like this one has a really nice hook echo here. And we got this one that has a little hook feature there, and these all have little hook features. And by the way, that's me, I'm right there. And so at the end of the day, this storm produced a tornado, and this storm produced a tornado. Why? Again, I don't know. So out of all of these storms, there's like 20 of them, if not more, on this particular radar image. It's sometimes just unclear. So hopefully that gives you a little bit of sensitivity to your poor weather forecaster who's trying to issue these warnings and say like, hey, I'm trying to keep you safe, but don't shoot the messenger kind of a thing, right? So it's very tricky. All right, next question. I get this one a lot. Are tornadoes becoming stronger and more frequent? So if we look at this graph here, our tornado reports start out right around 1950, and then this one takes it through 2022. And if you look at this blue trend line here, it looks like, yeah, maybe. So let's talk about that a little bit. All right, we got to be careful here. And the reason why we have to be careful is because this number count is not truly reflective of all of the tornadoes that have occurred throughout all time in the United States. So first of all, right here in 1972, this is when tornadoes were first formally reported. Prior to that, all of these other numbers, which represent the total number of tornadoes per year, these were all acquired from newspaper archives. So you can imagine if a tornado went through, Farmer Joe's field and just knocked down a couple corn stalks, it wasn't in the newspaper. So we're going to bias our sample by basically reporting the high-end tornadoes here, but missing the weaker tornadoes every time. So these are very underreported. Then, roughly about 1990, a brand new radar system came online for the whole country called the WSR-88Ds. And these, all of a sudden, enabled weather forecasters to see rotation. Prior to that, we couldn't see rotation. So from 1972 to 1990, we had intermittent, yes, we had actual reporting practices, but actually, I'm gonna tangent here a second. Did you know that it was actually illegal to issue tornado warnings or to even say the word tornado in some states prior to roughly 1950? And that is because it was thought that the panic incited by just saying tornadoes would do more damage than actually trying to warn for them. So there was a big stigma about saying tornadoes, and it was outlawed from the 1920s to roughly 1950, believe it or not. So you can imagine, again, there's going to be some problems with reporting practices if you're especially trying to extend things before 1950. All right, so radars came online here, and now we have entered the modern era, what we refer to as the modern era of the National Weather Service, which is basically things roughly according to the way they are now. So it's really most important to focus on this roughly 30-year period where we had radar availability, where we had national weather services that were all equipped with reporting and practices and receiving phone calls, et cetera. So if we look at all tornado events from F/EF0 through F/EF5 from 1990 through 2022, this is what you get. And it's pretty constant. There even might be a slight decline in the numbers over that 32-year period. So I'm going to come back to this one. So are tornadoes becoming more frequent? No. All right, going back and looking at our breakdown of the F/EF scale, and I didn't explicitly talk about this in the slides here, but this is the it's F/EF because prior to 2006, it was the Fujita scale, F scale. After 2006, some changes were made that basically allowed us to look at structures other than houses to assign damage ratings to. And that is the EF, or the enhanced Fujita. But one thing to note is that this is a damage-based scale. It's when a bunch of people come out, scientists, engineers, they look at the damage and they've assigned wind speed values based on the type of damage that they're seeing. It's nothing recorded, it's nothing observed. It's entirely based off of what the tornado did to the structures nearby. It used to be with the Fujita scale, this had to be houses. With the enhanced Fujita scale, now we can include things like trees and Walmarts and gas stations. And by the way, if you're ever at a Walmart, get out, because those things will go up with not even tornado strength winds. All right. So if we look at the most intense tornadoes, these F/EF5s, 4s, 3s, and even 2s, these strongest tornadoes have actually been declining over the past, this is looking actually at the full record from 1950 to 1922. So not even accounting for any kind of changes in population or reporting practices, we actually see those numbers going down. What we see go up are these weekend tornadoes. And the reason for that is because we are better able to identify them. So we're seeing more of these EF1 and EF0 tornadoes because we have improved capabilities to observe and detect and even verify these weak tornadoes. So we are not seeing more frequent tornadoes. We are not seeing stronger tornadoes even. So the change is that we are much more aware, right? 30 years ago, we didn't have people streaming GoPros in their cars chasing tornadoes. Right? We didn't have YouTube, we didn't have, we had the Weather Channel, so if the Weather Channel was lucky, then they were able to, maybe get some video piped into them from somewhere. But we're just seeing and hearing about them because we're much more connected now than what we ever were before. All right, so then that leads kind of naturally into like, okay, well, I've heard some people grumble like, well, what's the media feeding us? Like the media is creating the story that there's more tornadoes and more frequent tornadoes and they're worse and all of this stuff. How, and by the way, I'm not faulting the media. They want people to watch them and it's important to talk about these events. But the next sort of logical step to this is like, okay, well, what about climate change? And what's happening with tornadoes and climate change, and are they related? All right, little caveat here, this is not my personal work. I'm representing the work of others here. So I'm the messenger in this sense, and I don't want to try to take credit for something I haven't personally done. But we can't link individual tornadoes to climate change, and hopefully you can see why now, because those tornadoes are very susceptible to those localized conditions and the storms that produce them. So that makes it very difficult to create a link between something that's happening over 5 minutes over a period of land or a location of land that might be a couple miles wide with a big global climate scale that varies on the order of at least decades. But the thing that we can try to do is look at the environments of the storms and trying to predict some tendencies of tornado-supportive environments and look at how those environments are related to climate change. One other thing to note here is that, as I indicated, our tornado record is about 70 years, starting in roughly 1950, and it's arguable, like, that's not even a really good representation. Our best representation is only about 30 years long, from that 1990 mark to current. So in the context of thousands of years of temperature and precipitation records that we can successfully get, you can see that we really don't have a good, clear idea of what tornado normal actually even is. So we look at these environments and the tornado supporting environments and how those are potentially related to climate change. So what do we do, or what are we seeing when we're looking at those types of things? Well, what we're seeing is the amount of instability. So remember that cold air over warm, moist air at the ground. The amount of instability is actually increasing. So the numbers of days per year where we have this instability present is increasing. And that's a function of a warming climate where we have warmer temperatures, we have more evaporation that can occur. So we're promoting that instability scenario. But there's a flip-flop to that, and the flip-flop is that the number of days where we have that strong shear is actually decreasing. So that upper conditions are actually less favorable in a climate change scenario because those upper conditions are driven by temperature contrast between the poles and the equator. And under normal conditions, that temperature contrast is magnified, creating these waves high up in the atmosphere and these strong winds. Under global warming conditions, those winds actually start to get reduced because we're warming the poles in a way that's inconsistent with the southern latitudes. So we're actually decreasing that temperature change from the southern latitudes or the equator to the poles, and that is reducing the amount of shear that's present, or the number of days that we have strong shear. But when we have both the increasing shear, and we do have that combination of strong shear and instability, this is happening over a larger area of land than it happened before in the past. So we're creating this supercharged environment over fewer days of the calendar year, so it ends up that the net result of tornadoes is basically we're not changing the numbers. But what we're doing is we're concentrating our tornado events on fewer days, but having larger tornado outbreaks on those fewer days. So the graphs that I have over here are taken from a publication written by James Elsner, and it's looking at the number of tornado days where you have at least 4, 8, 16, or 32 tornadoes occurring. And this is pretty telling right here. The number of days where we're having at least 32 tornadoes is almost exponentially increasing. Same with 16. So again, we're reducing the days where we have like 2, 3, 4 tornadoes, but we're increasing at the expense of like one day producing a boatload of tornadoes. All right, another role that climate change appears to be playing is shifting the seasonality of when tornadoes are occurring. So we are seeing more tornado events in the fall and the winter months, and even kind of early spring, so specifically the month of March. And this is occurring especially in the Midwest and southeastern region of the US. And on the flip side of that, we're seeing fewer late spring tornadoes like May into June, and considerably fewer summer tornadoes. And this is also especially notable in the northern and southern plains. I will say there's a slight trend for increases of tornado events in the northeastern US over the summer. So this is feeding into this idea of another question that I get, which is Tornado Alley shifting? And the answer is maybe, and well, sort of. You like how I'm really like gung-ho and clear here? So what we are seeing, oops, press the wrong button. The tornado reports up here, these are total number of tornadoes, and a comparison between the 20 years from, I guess this is 30 years, I apparently can't do math. So between 1954 and 1983, and then comparing it to the 1983 to 2013 numbers of tornadoes. And if you can barely see the grays under here, this is a map of the US. Lake Michigan is here, Georgia's here, Florida's here, Texas is here. So what this study did by Ernest Agee, he looked at these two eras and compared, and we see that we're seeing more tornadoes occurring across Tennessee, Alabama, Mississippi, and to a lesser degree, even up into like the northeast US, and a decrease in the sort of traditional tornado alley area there. Now, I like to caveat this with the Central Plains are still the hot spot for tornado activity in the US, but the trend is decreasing there while it's increasing in the southeastern US. And then another recent study done by Victor Gensini and Harold Brooks in 2018 looked at tornado environments and the number of hours that tornado environments are favorable, or environments are favorable for tornadoes. And what their study found was that there is an increase, so this is comparing between 1979 and 2016, there's an increase in tornado frequency in terms of environments, again across the southeastern US and even up into the Central Plains. The black hatching means that this is statistically significant, and then the blue indicates a decrease. So again, less time that the environment is basically supportive of tornadoes across Texas and Oklahoma and perhaps up into Colorado, more time in Arkansas and Mississippi and Alabama, Tennessee, etc. So, okay, I didn't want to get there quite yet. So this again kind of gives you the idea that things are changing a little bit. So the net result ends up being kind of a wash, but there are some nuances in the distribution in terms of time, in terms of space, that likely are a function of climate change. So we do have that sort of broad scale picture that we can talk to. And one thing to note also is that the decreases here in the Central Plains are most certainly due to changes in the hydrological cycle, more drought. So it's drier, it's hotter, and when you have dry, hot conditions, you're not going to be able to produce the thunderstorms that produce tornadoes. So increasing drought across the central US is almost directly responsible for the decrease in the number of tornado events there. Okay. Here we go. So now we're kind of separating a little bit. Can you destroy a tornado or prevent one from forming in the first place? Some people are very adamant that you can, but unfortunately, the answer is probably no, at least to a reasonable person with morals and ethics, the answer is no, all right? So even if you could hypothetically destroy one tornado, the large-scale environment is still going to be supportive. You'd have to cover thousands and thousands and thousands of square miles with some kind of chemical to create this change in the large-scale environments that are ultimately what are supporting these tornadic storms in the first place. So shooting explosives into a tornado is not going to work, I'm sorry to say. Yeah, I mean, if you want to go try it, you might have some mad farmers because you'll end up blowing up some corn. It might disrupt the tornado for a moment, but again, think about the life cycle of these things. These storms that produce tornadoes are hours long. So even if you disrupt things for a moment, that doesn't mean that you're changing the large-scale environment in a way that is going to sufficiently disrupt the possibility for tornadoes downstream. And another thing is like, if we're playing God, we don't always know what the consequences are. We might be well-intended, but there might be unforeseen circumstances that we don't even think about. All right, how many people saw Twisters? All right, a good showing in the audience here. Glad to hear it. I'm on the bonus features, by the way. If you want to go get the extended version, I'm actually on it. Pretty cool. A little self-prop there. So in the movie, they have this plot to release absorbent material similar to a diaper into the atmosphere and evaporate the water and kill a tornado. So would this work? Well, I mean, hypothetically, I had a friend do the calculations, and he came up with something along the lines of 30 kilotons. So 30,000 tons of diaper material ingested into a storm, and maybe you can absorb all the liquid water out of it. I don't know how you're going to get 30,000 tons of diaper material into the atmosphere in the first place. And then what happens when it comes down? I don't know. Like, yeah, what goes up comes down, right? So there's going to be some unhappy wheat farmers there in the Central Plains. So really, again, you know, the environmental consequences likely outweigh our ability to do this successfully. So another thing that people have talked about to me is like, okay, well, what if we build walls? Okay, well, you're going to need a wall that's like taller than the Empire State Building, and it's going to have to go for thousands and thousands of miles in the north-south direction. Oh, and then you're going to need another one like about 20 miles down the road, and then you're going to need another one 20 miles down the road from that. And you got to create this almost like grid system. So the infrastructure support of that is absolutely not feasible. So, I mean, these ideas are well-founded, and I'm making light of it a little bit, but you know, we want to save lives, but the best way to save lives is really to get the science right and to provide our best ability to forecast these and to have people understand and listen to the forecasts and the warnings and the communication that's being delivered. Okay, so what is it like to be a storm chaser here? I'll kind of go through this maybe a little bit quickly because I do want to leave a little bit of time for questions here. We're approaching the end, but it's a lot of driving. So typically, we're looking at 400 to 500 miles per day of driving. So an average day is about 12 hours in the car. Sometimes it's 16. That's a lot. So where do we go? Well, we like to go to the central US. Nice clear skies, open land, and climatologically, we tend to favor severe weather here. It's good visibility. We can see what we want to see. So it's a combination of science, logistics, and luck, in all honesty. Like, you can be a perfect scientist and still not get to the perfect spot of the storm. Sometimes the road network stumps you. So that, for example, this is a county in Nebraska. This red square here is one county, and it is larger than the state of Connecticut. If you notice, there is 1, 2, 3 roads, one that goes this way, and then a couple little ones that spider around. So if you have a tornado right there, like, you are not getting to it in a car. So drones, okay, maybe, you know, but you know, it's possible. But you also need to consider other things, not just the weather. Gas stops, hail. Hail is a big thing. So you want to stay out of hail. You have to also consider about other storm chasers, et cetera. This is one of those roads in Cherry County, Nebraska. It's a beautiful country, sand hills, but there's really literally nothing out there. All right, typical chase day, you wake up, have breakfast, do a weather briefing. Back at OU, I used to do a storm chasing class with my students, so this is an example of when we were gathered in a hotel. Hopefully too calm here at OSU. It's just got to get the cogs moving in the machine a little bit, you know what I mean? That was an administration joke. All right, so we typically leave around 10 o'clock from the hotel, start driving, and we drive and we drive. Lunchtime, typically lots of fast food. Subway becomes your best friend because McDonald's after 4 days in a row is really gross. I don't know, maybe after one day, maybe after no days it's gross. I don't know, it depends on your flavor. And then typically after lunch, we're refining where we want to go. And then optimally, you're in position for storms to develop around 3 o'clock. And then you find a nice park and kind of relax, throw the football around or whatever, you know, hang out. It's always a hurry up and wait. You're waiting, there's nothing. And then it's all of a sudden, go, we gotta go. We're an hour away from where storms are happening. So you ideally observe convection from roughly 4 in the afternoon, maybe a little later, to whenever, 8, 9. The tricky part is once storms form, you have to figure out which storm to go to. So as I showed you before, sometimes we have scenarios where there's lots of potential candidates, and which one do you go to? All right, so that's us up here. There was a tornado report on this storm. We're trying to go down, figure out which one of these storms. All these other little dots are other storm chasers, so you also have to consider how many people are out there on the road also trying to find storms. So you're looking for things on visibly on the radar, hook echoes, swirls, like rotation on the velocities that show where mesocyclones are. You want to be mindful of all of these other chasers. And you want to be close, but not too close. So ideally, like 1 to 3 miles away is generally ideal. 1 mile keeps you kind of safe enough. 3 miles gets you back and can give you some nicer storm structure photos. You want to stay out of urban areas. This is an example from 2013. This is I-40 going east-west across Oklahoma City. With a catastrophic tornado, the widest ever recorded, bearing down on the city. There was mass panic and mass evacuation, and the highway system turned into gridlock. People were driving the wrong way down the highway. I was one of those headlights in there somewhere in a radar truck. So people go crazy sometimes in the face of these storms. And I can't fault them. There was a really devastating tornado that had happened there a week earlier. So this guy actually incited panic by saying you're going to die if you're above the ground. So, all right, he was a little bit more diplomatic than I just was right there. But basically said you can't survive this tornado above ground. So everybody left. Okay, stay out of the core. Thankfully, that's not my car. But this is a real hailstone that I saw in 2013. So this was over 5.5-inch wide hailstone. So all of this purple here is ginormous hail. You don't want to be there. This is me driving through a big chunk of hail. So not as big in terms of the size, but it's covering the ground. You literally get snowplows out here for severe storms sometimes. And as I indicated, sometimes there's loads of other people on the road. Here's another situation. All of those little red dots are chasers. So you have to be really careful about driving, about what's happening on the road. All right, so the reward. All right, here we go, more eye candy. Yay, tornadoes. This is a nice supercell with a wall cloud here, precip over here, updraft up there. Another little tornado in southwestern Oklahoma. I took all of these pictures, by the way, in my various efforts. This is one of my favorites. This was a Turkey, Texas tornado of 2007, rather. Sometimes you get these really cool low-hanging wall clouds, green indicating hail of roughly golf ball size reflects or refracts green. So you get these really interesting kind of green skies. Here's a really pretty one where you can see the updraft nice and clear here. Nice little kind of swirlies going on in the cloud here. And really pretty tornado as it was decaying at sunset. Sometimes like the sky turns this amazing color when you have storms at sunset, this like orange, and sometimes I've seen like a magenta pink. It's really, really amazing. Sorry if I just blinded you with a laser pointer there. Another one, this was across the high plains of northeastern New Mexico, so we've got some mesas there. And this tornado was from Wyoming, LaGrange, Wyoming in 2009. And then some of the most spectacular rainbows I've ever seen in my life. So after the chase, you eat dinner. Big Texan doesn't like it when a group of 16 people come in at 9:30, but they'll feed you anyway. By the way, the Big Texan, which is in Amarillo, Texas, has an eating competition. If you finish a 72-ounce steak, plus a salad, plus a dinner roll, plus your green beans, maybe, you get it for free. Otherwise, it's a $75 bill. So anyway, try not to chase storms after dark. It's too late. But last slide, coming soon, as Stephen alluded to, I'm the recipient of a University Good to Great grant. They're giving me money to procure a state-of-the-art, brand new dual pole, so dual polarization, phased array radar, lots of fancy words in there, nice and flat, and it does really cool things, and there's nothing like it currently in the meteorology community, so yay, OSU. All right, and I will stop there. We don't have a ton of time for questions, but John, I'll let you.
Let's thank Dr. Houser. Okay, so the way it works now is she'll take some questions. Typically, I'll ask her to repeat the question. And the other way we'd run things here is anybody who's a student, like a college student or especially younger, we call on them first, if any of them feel brave. But go ahead and throw a few hands up, and then we'll have questions, and we'll go to the reception. See a lot of hands. Okay, go ahead, young man.
We'll get you next.
So if favorable conditions are trending eastward, how would that affect the agricultural sector?
All right, good question. So the question is, if conditions look favorable moving east, so I'm assuming you're thinking of like the Midwest area, how will that affect agriculture? It depends. I mean, sometimes those fields really need the rain. I mean, the storms that produce tornadoes are also responsible for bringing a heck of a lot of rain too. That can be good, that can be less good. So especially as you transition out of the Central Plains into the Midwest, oftentimes these storms kind of transition from singular storms to lines of storms, and those lines of storms bring a lot of rain. But you can imagine too, the flip side of that is if you have really strong winds associated with the storms, this can also damage your crops. Great question. All right.
Go ahead, young man. Go ahead. Yep.
So, like, how do you collect the data in the storm? If you are going in the storm, how do you collect, like, the wind speed and all that?
So the question is, how do you collect the wind speed and the data in the storm? And the answer is using something like this, with a radar. So radars are really cool because they can like take x-rays of the storms. So you can basically take a radar and you can drive up close to the storm and you get a picture of the storm and what it looks like on the inside. You can see the distribution of rain, the distribution of hail, you can see what the winds are like, and that is really how we study these. Great question. Another question.
Oh, I see a million questions. Go ahead, ma'am.
So I recall with Hurricane Milton, remember in Florida, they had a few tornadoes that came out of that. So if climate change is causing more or more severe hurricanes, is there a sense that that could also cause then more tornadoes?
Right, so the question is, how are we linking hurricane-induced tornadoes to climate change potentially? And the answer there is sort of similar as before. So yes, at 100% climate change is promoting more intense tropical cyclones. Hands down, that is for sure happening. Doesn't mean that the tropical cyclone wouldn't have formed otherwise, but the increases in sea surface temperature are promoting much more robust and energized tropical cyclones. So with a landfalling tropical cyclone, that's when you have the risk of tornadoes that are induced by that tropical cyclone. So hypothetically, the link is a little bit nebulous, but again, like if your tropical cyclone is stronger, in some instances, and especially if it's wider, if it has a wide expanse away from its eye, there tends to be more tornado events occurring with these really wide storms. So you could maybe see a little bit of an influence of climate change through the tornado production of these stronger, more intense tropical cyclones.
Go ahead, young lady.
How do you identify a wall cloud? That's a great question too. So if we go back a little bit here, wall clouds are going to be, in fact, that was actually a good one to start with. So wall clouds are these low-hanging little areas of cloud that kind of come from the bottom part of the cloud. So the cloud base in general is a little bit flat, but then what happens is you get precipitation out here that causes some cooling. And as that cooler air gets sucked into the storm's updraft, it actually causes clouds to form at a lower height than what they would otherwise. So this is like a baby wall cloud. This is the one that's kind of starting to form. And then if we go back, this one doesn't have one. But here, all right, the base of the storm is roughly about here. But this is a really low wall cloud, which tells us that there's a lot of moisture in this air. And the air that's coming into the storm might be slightly cool as well. So it's this downward, almost like upside down table feature. Great question.
Go ahead, sir.
So, sorry I didn't see the second one yet, but I will. But in the first one, the issue of tornadoes shifting and you chasers getting more than you bargained for and having to get the hell out of there.
Yeah.
How often has that happened, and what causes tornadoes to shift direction?
Yeah, so the question is, when you have an ongoing tornado, in the original Twister movie, there was a scene where the tornado all of a sudden shifts. And actually in Twisters, there's something that kind of alludes to that process as well. Do tornadoes actually shift that dramatically in the field? Generally, not quite that dramatically. It's not like they're going like to the east and then all of a sudden they go back to the west. But what happens is that on the backside of the storm, you can get cool air that basically sinks down and it kind of burps out. And what happens then is it creates this surge of air that comes and kind of wraps around the tornado. And it can actually cause the tornado, instead of moving this way, to like from southeast or southwest to northeast, it curves it back around. And sometimes tornadoes even do like a little loop-de-loop at the end there because of this swirling outflow that's sucking the tornado kind of back in the back of the storm. Yep.
Go ahead.
What causes super deep ground scouring in tornadoes?
question is, what causes super deep ground scouring in tornadoes? So ground scouring is when you have typically some kind of debris that's being dragged along the ground itself. The tornado itself can remove, the vertical velocities in a tornado at the surface are sometimes incredible. In fact, I actually saw, there was a tornado that went through Greensburg, Kansas in 2006, and I saw a fire hydrant that was sucked up out of the ground with about 6 feet of pipe. So the tornado literally sucked it out of the ground. So sometimes it can be the immense upward velocities of the tornado, but more commonly than not, what it is it's debris that's being blown by the tornado winds and drug across the ground. So it's not quite airborne, but it's almost like a plow, and it's coming through and making these deep scour marks in the ground.
Go ahead, Miss.
Why is there hail in the tornado?
Why is there hail in the tornado? Another good question. Typically, there's actually not hail in the tornado, but there's hail outside of the area where the tornado is. And what happens is that updraft, that upward moving current of air, is so vigorous and so strong that it shoots water way, way high up in what otherwise outside of the storm is ice. So the water actually circulates around this spinning updraft, and it goes through this process of accumulating ice and then accumulating water and then going back out where it's cold and it refreezes. And if you have a strong enough updraft, it can actually create hailstones that are almost like basketball size, not quite, but like 8 inches big. And it can support that until the hail either gets too heavy and falls out, or its trajectory kind of shoots it outside of the area where it's that strongest upward motion is.
So many hands. Go ahead.
Hi, I was just wondering what you make of perhaps the increase in nighttime tornadoes, especially recently, like last night, some violent ones earlier in like 2020, 2021.
Yeah, the question is, what do we make about increasing nighttime tornadoes? And I don't know that we've actually looked at a true distribution of time of day in order to for sure, like I can't think of a study off the top of my head that has explicitly targeted the time of day. Nighttime tornadoes do happen. They have sort of always happened, but the question is, like, are there more of them? I don't know if there's more of them or not right now. I don't have that information. I mean, I could figure it out for you. Give me a couple days. Actually, don't hold me to that. I've got too much to do. But yeah, I mean, nighttime tornadoes require a sort of different set of parameters, and typically you need to have even stronger wind shear than what you have during the day. So you need to have that low level in the lowest couple hundreds of feet even of the ground really cranking, and that way you can take, because it's typically cooler at night, right? So we don't have quite as much like heat at the surface, so we need to compensate for that through that strong rotation. So that tends to, be why you can get nighttime tornadoes. I saw this hand for quite a while.
Sounds like a good research project for you.
Yes.
Go ahead.
What was like the highest end parameters you ever seen on a chase?
I saw the El Reno 2013 tornado, which my radar that I was in recorded the widest tornado ever in the history of tornadoes. So that tornado was 2.6 miles wide. We observed wind speeds that were over 300 miles per hour. And so that was my personal biggest tornado, which is pretty much the biggest one there was ever.
Miss, go ahead.
So there's a tornado that was the EF5 in Washington, did it actually with the lungs of cows?
Okay, so which tornado? The question was, did
Dead Man Walking?
Yeah.
The EF5 Dead Man Walking tornado?
Okay, I'm not familiar with which tornado that was. Did you say Gerald, Texas? Okay, so I do know Gerald, Texas. I cannot attest to whether or not it took the lungs out of cows. I'm sorry. I mean, a super strong tornado can do a lot of things. I'm not sure how the cows handled that, but I have seen pieces of straw embedded in concrete because of the wind, like just like a berm, for a sidewalk with straw sticking straight out. So, I mean, could be possible. Weird things happen.
Go ahead, ma'am.
Can you speak a little bit about the history, the purpose, and the current status of cloud seeding? as an industry?
Okay, history, purpose, and current status of cloud seeding. Well, I'm not a cloud seeding expert. What I can tell you is that it is done occasionally. It had its origins like way back, I think in the 1950s and 60s. Originally, it was to be a drought mitigation strategy. They basically put silver iodide in the environment, which acts as hygroscopic, so basically water is attracted to it. And the idea is to start to produce clouds and then ultimately get clouds to form and form precipitation. There are still some cloud seeding missions. I know like the United Arab Emirates and places out there still do this. I heard that some places in Canada, but I'm not 100% sure what the status is. I am not well enough versed on what's currently happening to feel like I can give you a confident answer on that, but that's about what I know.
Okay, let's take one more question. Go ahead, sir.
What are the variables that produce long track storms like maybe 500 miles?
What are the variables that produce long track tornadoes, the ones that are on the ground for 50 to 100 miles or so? Yeah, that's an interesting question, and obviously those are the tornadoes that we're most frequently interested in because those are going to be the ones that tend to be life-threatening. And really, it's like a 1% environment distribution, so to speak. So what do we need? We need that extreme low-level vertical wind shear, and that's really the most important ingredient. So there's evidence to suggest that even within like the lowest 100 meters or so of the ground, so 0 to 300 feet or so, if you concentrate shear there, then as the tornado is ongoing, what it can do is it can tap into the environment. So I said at the beginning that in order to form a tornado, we need ground-based rotation. When you have a tornado that's ongoing, now it sort of transitions like, okay, we had that ground-based rotation. What is going to cause it to be longer lived? And that is, it's going to be able to tap into horizontal spin in the environment and tilt it into the tornado.
Okay, I have 3 quick questions for the audience. The first is, if you haven't already signed up for the Science Sundays email list, I encourage you to do that. So all you got to do is open your phone and Google Ohio State Science Sundays. It's about a once-a-month email. You'll find out about events like this. So the question is, have you done it? You'll have a chance to do it in the next 10 minutes when it takes to get everybody out of here. Second question is, who would like to have a cookie? So we have a reception upstairs in the traditions room. So it's basically that way and then up. And then who would like to help me thank Professor Houser?